Take a look at these two renders. Both of these took the exact same amount of time to compute. The difference isn't a faster computer, it's better math. If you've watched Sebastian Lague's amazing ray tracing series, you know he built an incredible foundation. In his first video, he implements a material model that handles diffuse and specular surfaces. Next, he introduces a bounding volume hierarchy to speed up the computation. And in part 3, he explores glass and caustics. But since basic path tracing is incredibly inefficient at finding the light, we are going to fix that. We are taking his code and implement a technique called multiple importance sampling to optimize rendering. To understand the solution, we first need to look at how basic path tracing actually works. Imagine a ray shooting from a camera into the scene. When it hits an object, the engine has to answer a question. Where is the light source? To figure that out, the engine randomly picks a new direction inside a hemisphere above the hit point and bounces that ray. But in a large room with a single light, what are the odds that a completely random ray actually hits the light source? Almost zero. So how do we improve it? We stop relying on random chance and introduce multiple importance sampling. This optimization starts the exact same way. The camera ray hits the surface and we still sample a random ray to keep bouncing around the scene. But this time we do something clever. We send out a second ray, and this one isn't random, we aim it directly at the light source. We call this a shadow ray, and as long as there isn't a wall blocking the path, that shadow ray is guaranteed to reach the light. So, multiple importance sampling really just boils down to combining two techniques: standard path tracing and direct light sampling, which guarantees we find our light sources. We are going to build the second part first, and then we will look at the math required to merge them together. Let's take a look at our scene here. Under the hood, all of these models are stored in a single list that is called model info. Because our new routine needs to easily grab a random light source, we first sort this list by emission strength. So all the emitters end up at the beginning. Since our previous scene takes ages to converge, let's set up a split screen. We will keep the old method on the left and build our new method on the right side to see if we are actually making progress. Inside our new direct light function, we first choose a random light source from that sorted list we made. This mesh will be the target of our shadow ray. But these models are just collections of triangles. So we pick a random triangle from that light's mesh. After the selection, we must apply its transformation matrix, so we know exactly where it sits in our world. And the final step is picking a random point on that triangle. To get an exact point to aim at, we generate a pair of random UV coordinates and use them to interpolate between the edges of the triangle. We also calculate the normal for that point. Now our target is locked in. Afterwards, we just connect this function to our path tracer and send a shadow ray towards the generated target. If the ray reaches the light, we grab its contribution and add it to our pixel's final color. Alright, let's run the code. And okay, you might notice a very subtle difference. It is completely blown out. So why did our scene explode? To understand what went wrong, let's do a quick thought experiment. Imagine you are doing standard path tracing and you are at this point on the surface. Would you say that most of the rays will hit the light? Probably yes. But watch what happens when we move that light further away. Suddenly the probability of a random ray hitting it drops a lot. It becomes exponentially less likely. But look at what our new direct light algorithm is doing. It doesn't care about the distance of the light. It draws a line straight to the target every single time. To fix this, we introduce the g-factor, which brings two basic rules of physics back into our code. First, light spreads out over distance, so we divide our contribution by the squared length of our shadow ray. Second, light hitting a surface at a steep angle stretches and dims, so we scale it down using the cosine of the hit angle. We plug our new g-factor into the engine and... okay, the image didn't explode this time. but if we look closely, there's still a subtle brightness mismatch. It's closer, but it is still mathematically wrong. To truly fix this, we have to stop looking at race and start looking at probability. We need a more fundamental view on path tracing itself. But before continuing, please consider subscribing. There will be more interesting videos this year. Path tracing is just trying to solve one massive mathematical problem: the rendering equation. It's a beautiful formula, but it's a recursive, high-dimensional integral. Trying to solve it like a high school algebra problem doesn't work. We have to guess the answer. And to do that, we use Monte Carlo integration. Let's look at a much simpler example first. Finding the area under the curve x squared between 0 and 1. By hand, we know the exact answer is 1/3. But pretend this was impossible to solve analytically. How does a computer approximate it? An integral can be approximated by taking infinitely many random samples from a probability density function, inserting those samples into our function f, dividing by the PDF of that specific guess, and then averaging the results. Since that was a lot of abstract math jargon, let's ground this more concretely. We define the PDF as a uniform distribution. That means all numbers between 0 and 1 are equally likely to be picked. By picking 3 random values and doing Monte Carlo integration, we get an approximation of 0.53. Now let's try again with 10 samples. The result is 0.373. Better, but still not that close. But what if we don't guess blindly? What if we rig the game and tell the computer to guess more often in an area where the curve is actually the highest? This is important sampling. Generally speaking, when our probability density function resembles the shape of the curve we want to integrate, we get much better results. For this example, let's use a simple step function that guesses more often on the right side. We pick 3 random samples again, but notice, this time we must divide our result by the PDF to keep the math balanced. Previously, with the uniform distribution, we were just dividing by 1, so it didn't matter. Now we get an approximation of 0.32. That is incredibly close to our true answer of 1/3. To prove this works, I wrote a quick Python script to simulate thousands of runs. As you can see, the importance sampling approach consistently converges onto the true solution vastly faster than guessing blindly. Calculating this new probability in our code is actually quite straightforward. The total probability is just the chance of picking that specific light times the chance of picking a specific triangle divided by the surface area of that triangle. Inside our direct light function, we divide our light contribution by it. Let's run the renderer one more time. And perfect! Our implementation is finally mathematically correct. On the right side you can see the image converges much faster with almost no noise. By shooting direct shadow rays, applying our physical g-factor, and properly dividing the correct PDF, we've solved the problem. But before we celebrate, let's look at a scene with a mirror. Suddenly, our brilliant new direct light method falls apart. Why? Well, it actually makes perfect physical sense. Think about how a mirror actually works in reality. Light only reflects off it at one mathematically perfect angle. But remember, what our new direct light algorithm does, it completely ignores the surface of the object, picks a random spot on the light and forces a ray to go there. For a mirror, most of those paths are physically impossible. So we are in a weird spot. On diffuse walls, our new method is the absolute winner. But on perfect mirrors, that old and slow standard path tracing is actually vastly superior. And this is where the multiple importance sampling finally comes into play. In his incredibly impactful PhD thesis, a researcher named Eric Veach introduced a mathematical concept called the Balance Heuristic. It is one of the most important works in path tracing. The idea is to simply do both, but dynamically apply a weight to each method. The weight depends on both probability densities. On the left, the PDF for sampling the light is 2. One light, one triangle, and an area of 0.5. If we had used the standard path tracing method, the PDF would have been 1 divided by pi, since we would have sampled a random ray in the hemisphere. On the right scenario, the PDF for sampling the light is still the same, but the other PDF is much higher, since we can only sample a ray in a nearly perfect angle. And after applying the balance heuristic, you can see that on the diffuse wall, the direct light method gets almost all the weight, while on the mirror, the standard path tracing is preferred. Finally, we get a beautiful, unbiased result that converges incredibly fast for both rough and specular surfaces. If you need some more details, check out the code.